Hello, everyone. Thanks for coming. We have Walker Smith with us today. Walker is American. He's based in the Netherlands, and he's been with us for the last couple of weeks at the IRL, working on molecule sonification, correct?
Yes.
Okay. So welcome, Walker. Thanks for doing this today. Please.
Thank you so much. It's fantastic to be here. My name is Walker Smith, as you just heard, and I am a musical chemist, the world's first musical chemist. So I'm currently doing research. I've spent the last year doing research in the Netherlands at the Institute of Sonology, which is a computer music research center based in The Hague. And I'll be starting a PhD in computer music at Stanford University back in the US this coming fall. And today I want to talk about my journey through combining music and chemistry and eventually becoming a musical chemist. So I hope to answer three main questions in my talk today. The first, who am I and why am I doing this? The second, what would atoms and molecules sound like if we could listen to them? And the third, why should we care? Okay, I guess there's actually four questions. So as I've said, and I was interested in music and chemistry both from a young age. And when I started my undergraduate study at Indiana University in the US, I decided to do a dual degree in chemistry and in music composition. I don't know if you've heard the stereotypes of the Midwest, the United States, but it's pretty much nothing but cornfields, so there's not much to do. So I guess I decided I would keep myself as busy as possible by doing two different degrees. And a lot of people thought, that's a strange combination. Why are you studying both of these things? And I was inclined to agree with that. I think I was just interested in both of them, but it is quite an odd pairing. But the more I uncovered some deep-rooted fundamental commonalities between how the two fields operate. And I think both of these fields involve clearly identifiable elements. So in chemistry, those elements are literal elements and molecules that we combine in different ways and ultimately transform through chemical reactions to synthesize new materials. This is especially true in the field of chemistry I was working in, which was organic chemistry, where the goal is to make new molecules or find ways to make molecules that no one has ever made before. Now these three words I think are very important to chemistry, especially organic chemistry, but they're also really fundamental to music composition. And I sort of found the process of making a new molecule in the lab and writing a new piece of music to be very similar in some ways. So in music you have elements as well, only those elements are notes, chords, rhythms, melodies, harmonies. And the most amazing composers can transform a simple musical idea or musical phrase countless times to create almost infinite variations and ultimately synthesize those together to form a coherent piece of music. So I felt like these two fields shared a lot in common, but really I was more initially captivated by these kind of deep-rooted abstract connections between how the two fields operate, but that didn't necessarily mean that I had a way to truly combine them. So I started thinking about, is there a way to actually combine them? Could I make music from chemistry? Or could I use music to better understand and communicate ideas in chemistry? And that led me to this seemingly ridiculous question: what would molecules sound like? So of course molecules are way too tiny and moving around way too quickly for us to be able to hear, but they're doing a lot of things, right? They're vibrating, their bonds are stretching and bending, they're moving through space, there's all this motion, and what if we could translate that into sound? So in the chemistry labs I was working in in a specific area of organic chemistry called methodology development, where the goal is to develop new chemical reactions to enable specific kinds of transformations that could lead us to new molecules or easier ways to build molecules than we currently have access to. And a very important technique in this field is nuclear magnetic resonance, or NMR spectroscopy. So this is the same technique as, same technology as magnetic resonance imaging in the hospital. If you've ever had to if you've ever had the displeasure of having to sit in an MRI machine, you'll know they're incredibly loud. And this technique is really important for chemists because it allows you to understand the structure of molecules that you made and determine, did I actually make the thing that I thought I made, which is really important if you're trying to make new molecules or find new reactions. So how does this translate into music? So when you have a sample of a molecule you've just made and you put it inside of a nuclear magnetic resonance spectrometer, you get a series of different peaks here. And a chemist would interpret these different peaks as corresponding to atoms in different what are called chemical environments. So in this case, this is a hydrogen NMR spectrogram. So it shows different types of hydrogen atoms based on what other atoms those hydrogens are next to. And that gives you an idea of the structure of the molecule. But looking at this in a more abstract way, this is really just a spectrogram of frequencies versus intensities. Usually chemists don't really think about this because this frequency axis is scaled into this unit called parts per million, which is just a standardization thing. But really this axis is just communicating different oscillation frequencies of the nuclei of hydrogen atoms. I'll talk a little bit more about that in a bit. But the main takeaway is this graph of frequency versus intensity is exactly what you'd see in the sound spectrogram. So I noticed this common connection between sound and chemistry mediated by the data that I was working with. And I was also studying electronic music a lot of the time, how we can make music with computers and computer algorithms. And really, that view of music is just music as data, just a string of ones and zeros that you port into like an MP3 file or something. You can sort of look at sound as a stream of data, so why not turn the data sets of molecules into music? So I selected one of my favorite molecules. So this is a molecule named Hippolyte J, and it was very important to me because one of the graduate students in the organic chemistry lab that I was working in found a way to develop this molecule from scratch. So no one had ever made it, and he developed a really amazing synthetic method to create this molecule. If you want to try doing it yourself, here's how he did it. And so I thought it's a really structurally interesting molecule, and it had a lot of personal meaning to me. So I wondered what it would actually sound like. And I want to go back to this idea of turning the spectrum into music. So when I showed the spectrum earlier, that's the data that chemists analyze. But that's not the raw data you get from putting your sample inside of this nuclear magnetic resonance machine. What you actually get is a time domain waveform. So there's initial excitation. So basically the nuclear spin of the hydrogen, the hydrogen's nuclear spin rotates by 90 degrees and then relaxes back to being in line with this magnetic field. And then you can do a Fourier transform on that data to see the individual spectral peaks, which as a chemist you'd interpret as different atoms. But this basic data is just a time domain waveform, which is exactly how you can represent sound. And in fact, what you're looking at now is not this data viewed from some sort of nuclear magnetic resonance software, or like analysis software. You can do that. But this is actually the data as an MP3 file. So each point is just a single point on this time versus amplitude axis. So let's listen to the actual sound of the molecule Hippolyte J. So brace yourselves because this is pretty epic. This is the sound of a molecule. Did you miss it? Here it is again. So that's what 3.5 years of chemistry research sounds like. So these, it sort of makes sense though, right? When we look at this shape, it's an initial excitation that relaxes very quickly. So it's a very percussive sound. And these atomic excitations and relaxations happen very rapidly. So we can't really hear a lot of details in the sound. But we can by slowing the sound down. So if we play it at 10 times slower, we can effectively hear more of the nuances in the sound, so to speak. So let's listen to the same sound slowed down by a factor of 10. And it actually sounds quite interesting, I think. It's sort of like a molecular gong or bell or something. And the cool thing is different molecules sound slightly different. So there's some other molecules that were synthetic precursors to this one. So some of those might sound like, here's a third one, and a fourth one. So I think you'll agree that the differences are subtle, but we can hear the differences, although they might be very small. We can hear the differences between different molecules, and the sounds are just already interesting by themselves. So before I talk about the path that I went on to sort of turn these into a musical composition, I want to take just a momentary step back to ask, why would you want to do this? So this basic idea is rooted in this idea of data sonification, which is the representation of scientific data through sound rather than traditional data visualization. And this has been shown to have a number of applications in chemistry and other fields as well. The first really exciting application is accessibility of these data sets to blind or visually impaired students or researchers. There was a really interesting study about 10 years ago in the Journal of Chemical Education where researchers developed sonifications of infrared spectra and showed that students were able to, after a learning period, differentiate between different molecules purely by listening to them. And they actually found that these were almost as effective, or in some cases even more effective, than tactile methods such as Braille. But even aside from that, auditory representations of data can add an additional layer to traditional data visualizations. And that's really what I've spent the past few weeks working on in the Intangible Realities Laboratory with Christian, Harry, Ross, and Mohammed, and the amazing people in the lab. We're trying to see if we can turn molecular dynamics, so the real-time behavior of molecules, into sound to gain more information, particularly information that's difficult to communicate and express visually. So these are some applications, but I was really drawn to just the performance aspect, or this idea of using this combination of music and science as a tool for reaching the public and communicating science through musical performances, and also for developing educational applications that are in this area of what's called STEAM, so STEM being science, technology, engineering, and math, and then you add in the arts and you get STEAM. So that's a really exciting area of work. And these last two red points are where my work has sort of gone in the past few years. But I'm jumping ahead a little bit because I want to get back to what I did with the little molecular bings and bongs that you just heard. So I was doing this research in a class that was called Individual Projects in Electronic Music at Indiana University. And the goal at the end of this class was to premiere a musical composition. So we set up a big multi-channel sound system with 8 speakers all around this big concert hall. We spend the whole day setting up, and then everyone premieres their compositions. Some of them are electronics with acoustic instruments. Some of them are a performer on stage with a laptop, like live generating sound with code. Some of them might not even have a performer on the stage. It's just 8 speakers in the audience, and the lights are out, and you're just listening to this surround sound experience. And so that was the task that I was charged with, was developing an interesting musical composition based on these molecular sounds. And I really had 3 goals that I wanted to achieve. The first was this science communication idea of actually teaching the audience something about the chemistry and about this connection between chemistry and sound. The second one was making an interesting piece of music. And the third was making this engaging to people outside of my very niche areas of organic chemistry and experimental avant-garde electronic music. Because if the only people, if I only reached people who were interested in both of those things, then I would probably be the only person in the audience, and I wanted more people to show up. And I was really mostly captivated actually by these first two. So I initially didn't really care much about making an interesting piece of music, and I really more cared about delivering an interesting presentation and teaching the audience about the connection between sound and chemistry, because I thought that was already really interesting, just the idea that you could listen to the behaviors of molecules. And it was really important for me that the audience walk away with this understanding. I was wary of doing something that would kind of hit both of these points. So something that was a musically interesting piece, and maybe it also was engaging to people from various different backgrounds. But I felt that if I didn't communicate the underlying science or the underlying idea, I sort of missed an opportunity to elucidate something that I think is really profound. So one of the problems with or this isn't necessarily a problem, but I alluded to this idea of transformation earlier. And in music composition, especially in electronic music, you can basically turn any sound into any other sound. You know, I could take those little molecular bleeps and bloops and pass them through distortion and filters and all sorts of computer algorithms and make any sound I wanted, and then I could put those sounds together and make a musical composition. And it might sound cool. But I felt that if someone listened to that and thought, okay, yeah, that was a cool piece, and I guess the sounds came from molecules or whatever, sure. Or if maybe they didn't even read the little notes I'd written in the little program booklet, because people don't always read those at concerts, then they might not even know where the sounds came from. And that felt like a missed opportunity for me. So I went to the professor of this course, and I said, I've figured it out. I only want to do these two, so I'm just going to give a lecture. It'll be a very exciting lecture. It'll be very engaging, but I really just want to teach the audience something and play these sounds, and I don't want to compose a piece of music. And he said, great job, I am so glad you figured out what you wanted to do, but you absolutely cannot do that, because this is a concert, and you can't just get up and give a talk. If we let everyone just give a talk about their piece, then it'll go on forever, so you can't do that. You have to make an interesting piece of music. So basically, if I wanted to do these two, I had to do all three of them. So to reframe this problem in terms of the three words that I pulled up earlier, these are the three elements that I was working with, and I had to synthesize them together. And that necessitated some kind of transformation. And the transformations that were really essential for getting this to work were taking these molecule sounds that I had, the elements of my musical composition, if you will, and actually making a piece of music out of them. And in a way that I didn't feel was completely arbitrary, because again, I can do any sort of distortion or programming or whatever, and I can turn these sounds into anything. But I didn't want to lose the connection to the underlying chemical ideas or the underlying data. And then also, I had to somehow teach the audience something, but make it into a concert. And so going back and forth with this professor a couple times, we sort of both came to the same idea at the same time, which was, what if it starts out as a really humorous, engaging, sort of popular science lecture, and then morphs into a performance? So that's when I came up with the idea for The Sound of Molecules, which was my first musical chemistry composition. And I appeared as the character Maestro Molecules. So instead of presenting as myself on the stage, I dressed up as this pseudo-Einstein character with these 4 pins. The pins are very important. And I provided a sonic tour of the molecular world. So there's a very important shift in this piece where it transitions from being this kind of high-energy science lecture to almost this sort of narrative guided meditation through this science fiction molecular sound world. And I'll play some excerpts of this. The full video is available on my YouTube channel, which is called The Chemistry Shack, but I'll have links for that at the end that you can scan with your phones if you want to watch more. So let's let Maestro Molecules, should we dim the lights a bit? Can you guys see this? Let's see. here? Let's see. Okay. So let's let Maestro Molecules take us into the molecular world. In order to hear all of the details of these sounds, we need to zoom in. So I'd invite you to join me as we shrink down to the size of an atom and listen to these molecules up close. Now we've entered the molecules world. Let's hear that sound again, but up close. At this level, we can hear all the nuances of the sound as it decays. And here's another short excerpt from slightly later in the piece, where I manipulated these percussive sounds of the nuclear magnetic resonance data to create the effect of an electron buzzing around the nucleus of an atom. This stillness is interrupted by some molecules off in the distance. And we may even hear some other molecules nearby. As we get super close to these molecules, we can even hear the buzz of the electrons whizzing around the nucleus. So I should just clarify that this electron buzzing sound is in no way a literal sonification taken from data of electron movement or orbitals or anything. It's just manipulating the original nuclear magnetic resonance data and creating this effect of an electron. So really, it's just me having fun as a composer, and there are other things in the piece representing different chemical phenomena. So later in the piece, there's the sound of a crystal being violently dissolved in a solution, or an exothermic chemical reaction heating up and getting way out of control. And all of these are purely creative representations, but they're all originally based on some kind of manipulation of the original data from the molecules. And I also feel that I also discovered that this incorporation of this spoken narrative really helps guide the audience towards understanding and imagining these ideas while seeing the connection to the original material. Another thing that was really exciting about this was getting to play around with this immersive audio. So in the original concert, we had 8 speakers set up all around the audience. So that electron buzzing sound actually fully circles the audience. So it's a really cool experience. And when I've done this performance, so you get to really feel like you're inside of an atom. And the coolest thing is when I've done this performance for younger students, especially like the kindergarten or 1st and 2nd grade age, they're always like, as soon as the multi-channel stuff comes on, they're always like standing up out of their seats, jumping around like, wait, there's sounds behind me? Whoa, which I think is adorable and awesome. So I was very fortunate after this first performance, which was about a 15-minute piece that I premiered at Indiana University, and it attracted a lot of people, not only from music and chemistry, but all over the College of Arts and Sciences. People came to see this wacky guy in a costume doing molecule music. So I received a number of grants to develop a longer 1-hour version of this performance and turn it into this music science show at this science museum called Wonder Lab in Indiana. And it was then that I came up with this rainbow character whose name is Roy G. Biv, which is a result of it's an American acronym for the colors of the rainbow. In the UK, they have a similar one, which is Richard of York gave battle in vain, but I think that's a bit long. So I liked Roy G. Biv better. And I've also been told that there's no Spanish or Galician equivalent of this for the colors of El Arco Iris. But if someone knows of something, please tell me, because I would love to find out how to translate Rainbow Man into Spanish. So Roy G. Biv is really curious about what light sounds like. So the idea of listening to light might also sound as crazy as listening to molecules, but light and sound are both wave phenomena. Light consists of electromagnetic waves, whereas sound consists of pressure waves oscillating through a medium, typically air. And these are fundamentally different types of waves, but even if we could pretend that light waves were sound waves, we still wouldn't be able to hear them because the frequencies of light waves are 400 to 700 terahertz, way higher than the 20 hertz to 20 kilohertz, or 1 hertz is 1 oscillation per second. So the range of sound waves is about 10 to the 12 times lower than electromagnetic waves. So to convert electromagnetic waves, to convert the frequencies of visible light into frequencies of sound that we could hear, I had to develop a special scientific instrument that I call the Light Soundinator 3000, and I brought it with me today. So this device converts the frequencies of visible light, which we see as different colors, into musical frequencies that we hear as different musical notes or pitches. So red has the longest wavelength, or the lowest frequency, depending on how you want to look at it, of visible light. So it would sound as the lowest musical frequency. And then violet has the highest frequency. So if I go from red up to violet, we can hear the frequency of the notes gradually increase. Splendid. Now, another thing that I really love about this analogy is that it's actually really scientifically accurate. So violet light, and what I mean by that is that light contains, visible light is of course only a very small part of the electromagnetic spectrum, and it's pretty much 1 octave. So in music, 1 octave corresponds to a doubling of frequency. So 4 hertz to 8 hertz, or 20 hertz to 40 hertz. These are all octaves. So an octave in music sounds like this, which actually, now that I'm realizing this, are the first 2 notes to Somewhere Over the Rainbow. Somewhere, I shouldn't sing, but yes, everything is rainbows. So the violet light is just shy of double the frequency of red light. So that means that actually placing these frequencies of light into 1 octave of a musical scale is actually pretty close to being scientifically accurate. It might not be these exact notes, but I find that pretty interesting. And another really interesting connection is that this goes way back, this association of different colors to the different notes of musical scales. So Isaac Newton, in his 1704 optics, actually included this musical diagram, or this. It's a color wheel, because he was sort of the first person to come up with this color wheel after discovering the colors of the rainbow, and. But he also included this really speculative association of different colors to different musical notes. So it's not the same exact scale I played. It actually would start as red on this note, like red, orange, yellow. But it's the same idea, placing these notes in 1 octave, and he's starting with red as the lowest and then going all the way around to violet being the highest. And what I find fascinating about this is that Newton did not measure the frequencies or the wavelengths of visible light. That wasn't done till about 100 years later by Thomas Young. So I'm still digging into this because it feels like just an insane coincidence. But these associations go back even to like the medieval periods, the ancient Greeks. So I'm not entirely sure what's going on here, but I'm trying to get to the bottom of it. But I just find it an absolutely amazing either coincidence or but the point is this association between sound and color definitely goes way back. And even though I invented the highly sophisticated Light Soundinator 3000, I'm not the first person to think of these sort of associations. But we can apply these to chemistry. So we can atoms and all the color in the world comes from chemistry, really, from elements and molecules absorbing and emitting specific colors of light. And we can make elements release light in a number of different processes by giving their electrons sufficient energy. So this is a device called a spectrum tube, which is a tube filled with a gas, and in this case it's helium gas at a low pressure with a very high voltage of electricity going through it. And that electricity gives enough energy to the electrons in the helium atoms so that they move up from a ground state to an excited energy state. So they gain energy and then eventually release that energy as light, some of which is in the visible portion of the electromagnetic spectrum. So when you do this for helium, you get this really pretty sort of magenta color. But helium's not releasing one magenta wavelength of light. It's actually releasing a whole spectrum of light. So just as we could pass white light through a prism and get all the colors of the rainbow, if we pass this helium spectrum, this helium light through a prism, we see that it's not actually this single magenta color, but it's actually this broken rainbow, these several discrete colors that blend together into what our eye perceives as a single color of light. And we can apply this light to sound mapping, where according to the Light Soundinator 3000, by basically associating, just literally taking the frequencies of each of these lights and dividing them by a very high factor, like 10 to the power of 12, so that we hear red light as a pure frequency, what's called a sinusoidal wave, and then the frequencies of yellow light, the frequencies ascending until we get to violet light. So in this case, we'll hear 7 different frequencies corresponding to the individual notes here. And so the frequency of the sound, the frequency of each sine wave you hear corresponds to the frequency of the light, and the volume of that sine wave corresponds to the brightness or the amplitude of that light. So let's take a listen to all of these together, which is a chord representing helium. I think it's a bit quiet, but you can still hear it, right? Okay, let's see. So yeah, okay. So I was really amazed that it's actually a pretty pleasant sound, just taking this very simple mapping procedure, not really doing any sort of music with it at all, but literally just translating the frequencies of light into sound. You get a nice musical chord. And we can also listen to these lines sequentially as a melody. So that's what this would sound like. So that is the helium scale, if you will, and this is that same scale notated in a traditional Western musical staff notation. So this is basically just a frequency versus time axis. The time here isn't really relevant, but I've just spaced them out according to their actual physical spacing in the spectrum. And one thing that's interesting, so if you have a very astute ear, you might have heard that those sound like a little bit out of tune, and that's because none of these actually correspond to actual notes on the piano. So nature doesn't care about, we've decided in the Western world that we have 12 notes in an octave. We're going to divide the octave into 12 notes, and that's for a number of reasons, but the chemistry doesn't care about that. So there's these numbers below that tell you how far above or below these individual notes are from the notes on the piano, which are notated here. But yeah, if you wanted to play this on the piano, you'd have to manually retune every string to get the perfectly in tune sound of helium. And every element has a unique what's called atomic emission spectrum. So these are the lines released when you give the elements enough energy in some way to excite their electrons, and then their electrons release that energy as light. Again, some of it is in the visible spectrum, and the specific frequencies you get correspond to the distances between the different orbitals in the atom. And yeah, every element has a these really beautiful broken rainbows for all the different elements. And this is actually where the colors in fireworks come from. So like green fireworks usually contain barium or copper salts, because when excited, those spectra contain a lot of emission lines in the green part of the spectrum, so they look green to us. And you may also recognize this from this flame test demo that's done with Bunsen burners in chemistry classrooms. Again, this is using heat to excite the electrons instead of electricity in the form of a high voltage, but it's the same idea. So let's listen to, so helium's the second element to the periodic table. Let's listen to the simplest element, hydrogen, which only has one electron and only has four of these electron transitions that release frequencies of visible light. So let's hear hydrogen. So it makes an even simpler chord. Again, sounds very musical. And at this point, I wanted to hear what all of the elements would sound like, especially the really complicated ones with hundreds and thousands of lines. So I found this really amazing website, and I'm including a QR code here because you may be interested to have a look at it. This is an interactive periodic table of spectra. It's a really amazing website that was put together by this chemist and photographer by the name of Julie G, who photographs spectra and creates digital recreations. And this site was really amazing. Excuse me. This site was really amazing for me because it not only contains these high-resolution images of all the spectra, but also complete data sets of people who have measured these spectra and calculated the exact frequencies of light emitted and their exact amplitudes. So that enabled me to construct this, the musical periodic table, which is an application I've been working on that allows you to click on an element and see a visual display of the spectrum, but also hear a sonification of this spectrum. So let's listen to a few other elements. So this is one. This is oxygen has 187 lines, more or less, and it sounds. You'll notice it sounds much more dense and noisy and less like a musical chord. So it's really hard to sort of pick out a few frequencies here because there's over 100 different frequencies packed into a single octave. So on a piano, again, you'd have 12 notes as a single octave. So imagine cramming like 180 keys in that same space and just smashing them all with your hand. It's an incredibly dense barrage of noise. And if we go to an element that has over 1,000 lines. So iron has actually almost 2,000 lines, so about 10 times as much as oxygen. It actually doesn't sound all that different. So this is what iron sounds like. And I think you'll agree that it's not that much different than oxygen. They're both kind of these different shades of this kind of noisy, this rough, noisy sound. And that's because we're sort of, you're sort of overwhelming one octave of the human ear with all of this frequency information. Now, humans can actually hear well over like 9 or 10 octaves. So I've recently been working on ways of stretching out these spectra and applying different sort of mapping procedures to enable us to hear more of the details in these sounds. And their results are a bit too preliminary, but I have seen some I've seen some cases where different mapping procedures can lead to people being able to identify these spectra more easily. But that's actually more in the sort of domain of accessibility and using these as a tool for scientific research, which I am becoming increasingly interested in. But really my work for the past couple of years has been focusing on using these materials as a composer and performer to share the sounds of the molecular world. So I really felt compelled to keep these sounds in their original form and use them as musical material, rather than going straight to thinking about it as a research-oriented thing of how can we identify all of these different elements. So that's definitely something I'm interested in and continuing to work on. But for in most of my work so far, I've really kept these sounds just the way they are, or using them as raw musical material. But that being said, even with this very basic literal transformation that just takes different frequencies of light and maps them into sound in a one-to-one correspondence, you can still sort of actually discern some chemical properties that you can actually hear. And one of the things that I find really interesting is this element, zinc. So zinc wasn't really on my radar before, like, listening to it, but now it's become one of my favorite elements because it sounds so awesome. And the reason it sounds awesome is because the elements around zinc in the first row of the transition metals they all look and sound pretty much like iron, these very complex noisy spectra with thousands of lines. And that's because they have this specific shell of electrons called the 3D shell, and they all have what's called an incomplete shell. So this shell of electrons can hold 10, but they have less than 10. Less than 10 electrons, so there are vacancies in this shell, which creates a lot of opportunities for electrons to jump around and have a lot of different energy transitions, leading to thousands of different lines like we see in iron. But zinc is different because it has all 10 of these electron all 10 of these electron slots filled, so there's much less mobility. Zinc this results in very different chemistry for zinc. It doesn't make as many pretty colors as the other transition metals, and really doesn't behave it doesn't really behave chemically like a transition metals, exhibiting a lot of the properties that other transition metals have. And we can see this with the spectrum, but I think it becomes, with a relatively simple spectrum, but I think it becomes even more apparent when we listen to it, because in contrast to the noisy, grating sound of iron, zinc sounds like a sort of choir of angels singing with vibrato, I think, is my poetic description of this sound. And I think that's really fascinating that even without any dressing up or any complicated mapping procedure, we can already start to discern some chemical properties and differences in the different elements. But I want to go back, actually, to way at the beginning of the periodic table, back to helium. And let's listen to that helium scale that I played before. Let's listen to that again. So, in contrast to my first composition, The Sound of Molecules, where I had these nuclear magnetic resonance pings and pongs, and I wanted to build a musical composition out of those, but it was very hard to figure out how to communicate these ideas to the audience and also to turn it into an interesting piece of music. The helium scale, these sounds of helium are already so musical that the piece kind of just wrote itself. And I'm sure you guys already saw this coming, but the only thing that this was asking for was helium dance party. I mean, obviously. So this is an audiovisual composition I created that became the second half of my Sound of Molecules show. And so you'll see the spectral lines of helium flashing on the screen, synchronized to the actual sound frequencies that correspond to those colors. And I also moved them into different octaves to create a bass layer and then like some mid-range chords and a melody. And there's also some special guest elements that make an appearance later on. So let's listen to the helium dance party. But I will warn you that you should buckle your seatbelts because things are about to get elemental.
some other elements to the party. Hit it, hydrogen!
Let's a round of applause for the can we have another round of applause for the elements themselves, because they're the real musicians here. So thank you, helium. Thank you, hydrogen. Again, the full video of this performance is available on my YouTube channel, and I'll have a QR code for that at the end. So this performance that I developed in this Sound of Molecules show, I've had so many wonderful opportunities to share this in schools and museums across the U.S. and in many places in Europe as well. This is a performance I did at a school in southern Indiana with an audience of like 500 middle schoolers, and they're all participating. I was asking them questions, and there's me over there. And I eventually worked my way up to doing a show at the American Chemical Society National Meeting in San Francisco last August. This was actually really cool because the theme of the conference that year was harnessing the power of data. And I think what better way to harness the power of data than make helium dance parties? I also presented my musical periodic table here, and they picked this up in a press release with a really awesome video on YouTube on the American Chemical Society channel. And the video, I think, has like 40,000 views now. This press release, so like a week after the conference, this press release was picked up by like 50 news outlets across the U.S. and also many places in Europe, a few places in Brazil, and then in the U.K. And there was even an article in Spain in the Europa Press science section last year. So if you happen to be reading that and haven't made the connection yet, I'm the guy. And I had I think my favorite show that I've been able to do was at this nonprofit, or this high school science arts festival called the STEAM Leadership Conference, organized by this nonprofit organization called the Project Fibonacci Foundation in New York. I performed here last August, and I was so thrilled to meet so many amazing high schoolers that had spent all week performing, attending performances and presentations and doing workshops and working on projects aimed at blending the arts and sciences. And I was one of the closing performers, and I met the head of the festival and the chair of the foundation, this guy, Andy Drozd, who's a wonderful human being, and he told me, I think what you're doing is more than sonification, it's personification. And I love this because I'm a sucker for a good pun, but I think it's actually a really great term for what I'm doing. There have been a number of terms developed around different ways of approaching sonification. One of them that I like is musification, which implies making music from data rather than actually holding steadfastly to any sort of rigorous data mapping and interpreting things musically. But I feel like that's not exactly what I'm doing, because I am retaining a deep interest in the data itself and in communicating that to an audience. But I think my approach centers more around creating a personal connection with the audience through the use of characters and narrative and storytelling, and really this, again, the science communication part, where the important thing is not just to create an interesting musical experience, but to actually teach something. I also like another aspect of this, which is, so it's actually a pun It's like a double pun because it's a pun in terms of chemistry too. So this prefix per in chemistry often denotes the highest level of something. So if we have a molecule containing only carbon and hydrogens, it would be called a hydrocarbon. And if we replace one of the hydrogens with a fluorine, it becomes a fluorinated hydrocarbon. But if we replace all of the hydrogens with fluorine, it now becomes perfluorinated. So I like, the highest possible level of fluorination. And I like this idea that it's the highest possible level of sonification. And I really leaned into this in my a recent piece that I premiered in the Netherlands titled Orchestra of the Elements. The video is still being edited, but it will be up on my YouTube channel in like mid-July, so stay tuned, subscribe. But in this performance, I really began to think of these individual scales or these spectra of the elements as the sort of like the alphabet of each element's unique musical language. So each element now has its own alphabet, and they can communicate with the other elements and with me as the performer. So I had conversations with the elements on stage. I also I ended the piece with this what I call the magical chemical forest. So maybe I should explain that. So I took this idea of flashing lights synchronized to the elemental sounds and translated them, basically added some slight what's called frequency modulation, which turns like a static sound like doo into like drrr, and you can get these really like bird chirp type sounds. So I took this idea, but instead of creating a helium dance party, I created this like chemical forest where I was having conversations with the different elements. And that's sort of the direction that I am moving in recently, of trying to actually communicate with the elements or establish this idea of a musical language. Let me go forward from here. So I should say I do have an excerpt of the performance, and I feel bad for like teasing it and not showing something, but there were some audio problems with it, so maybe if there's time at the end, I'll show like a excerpt from that. But for now, I want to close by returning to how I introduced myself at the beginning. So I said that I'm a musical chemist. And this is, what I have come up with to describe the work that I'm doing. But I think it's fair to ask, is chemical musician maybe a better term? Because I'm really, this year I've been at an electronic music institute, and I'm about to start a PhD in computer music, which although I'll be doing projects at the intersection of music and chemistry, I've really sort of firmly situated myself in the music domain, and I am a musician and a composer taking inspiration from chemistry and chemical ideas to create music. So maybe chemical musician is actually a better term, but I actually like this term musical chemist, because it forces me to ask this question, is what I'm doing chemistry? And I think the answer is yes, but not because I am working with data sets of atoms and molecules, and I'm working with the elements that constitute the field of chemistry. I think this is chemistry in a much more abstract way. And to sort of explain that, I want to talk about my whole artistic practice as a composer. So over the years, I've really been interested in combining a lot of different things into the music that I write. And obviously, especially in the past few years, one of those things is chemistry. But I also write plenty of music that has nothing to do with chemistry. I take a lot of inspiration from a variety of musical genres, from visual arts and color theory, from literature and storytelling, and also from food. And I want to elaborate on this last one, because in November, in November of 2023, shortly after I arrived in the Netherlands, I made my Dutch debut with a performance titled "I Am Eating a Bag of Chips" for amplified potato chips and live performer processed by electronic computer algorithms to generate different sounds. And this was kind of an interesting, discovery. It was really more of a joke. I was eating chips, and someone said, "Those are some really interesting sounds. You should make a piece out of it." And I said, don't give me ideas. I'll do it. And so I premiered this piece, and food has always been, like all these other things, you know, these are all very important parts of my life. Food is also extremely important. I love cooking and baking and learning about new foods and trying new recipes. So to make a piece of music based on food, I realized that this synthesis of chemistry with music is actually part of a much bigger whole, which is just taking inspiration from a lot of the different aspects of life that I find fascinating and working them into my musical expression. And also, just for those who are keeping track of the things that I've been interested in so far, we have chemistry, composition, computer music, colors, and chips. I guess I should also mention that I grew up playing clarinet and classical guitar, so apparently I'm only interested in things that start with the letter C, which I guess is why I'm here in Santiago de Compostela. That's all right. So yes, I think what I'm doing is chemistry, because if we go back to how I defined chemistry and music at the beginning, we can think of all of these red dots as the elements that I am transforming together to create a synthesis in my artistic practice. Or perhaps even better than that, these are the elements that I am synthesizing together to affect a transformation in the way that I look at the world, and hopefully communicating that with other people to transform the way they look at the world and the way they look at how things are connected. So I think what I'm doing is, what I'm doing is still chemistry, but I've moved from doing chemistry with atoms and molecules in the lab to doing chemistry with my life and trying to make music with that chemistry. Thank you so much, and I'd be happy to take any questions. I'll put up the links up there so that you can stay in touch and see my the bird magical chemical forest piece will be up on YouTube very soon. So please check it out. But yes, I'm more than happy to take any questions. Do we need to pass around a microphone, or is it fine to?
Great talk. That
Thank
was
you.
very entertaining. I have a question about the spectra of the different elements that you get with the vertical lines of light. So you said that in hydrogen there are 4 lines that appear, right? Mm-hmm. But presumably those 4 lines are only the excited state to ground state transitions, right? There are no excited state to first excited state.
They actually are the, I believe they're the excited state to, I believe they're the transitions of higher excited states to the first excited state, actually. Right. Because transitions, you can't have those. The transitions from the excited states to the ground state are much higher energy, so they show up in the ultraviolet region.
Right. Okay.
Yeah.
Super cool. Very nice. Thanks.
I have a question back there, I think.
Yeah, so thank you very much for your talk. It was quite amazing, to be honest. So basically you made music with the spectrum from the atoms or molecules. How would you consider it making music from the spectrum of stars, for example, or other things like that?
Yeah, I have. It's funny because I've actually. So the question was if I've considered making music from the spectra of stars, and it's funny because I've actually talked to astronomers about this because I came with this idea. I presented at this conference last year called the International Conference for Auditory Display, which is a conference for people who are interested in turning data into sound for various purposes. And there's a lot of astronomers. This field of sonification is biggest in astronomy, and astronomers are really good at it, at making like really awesome, amazing music, like with coupling the amazing pictures of the universe with musical representations of those. And it would definitely be possible to make sonifications based on the spectra of of stars, and some people have done that. One of the issues is that you don't get these very clean lines like you do, because these clean lines are from very controlled laboratory experiments, and in stars you get very continuous spectra, so it becomes a lot more like the noisy kind of spectra like iron that I showed. Of course, you can do different kinds of processing, but yeah, it is amazing on many levels how astronomers are able to parse out that data to begin with, just because you can. It's such a mess of all these different frequencies of light, but they can still, parse out like the hydrogen and the different elements. I did have an idea for like a composition that would be the life cycle of a star. So initially, if you would hear only hydrogen and helium, and then as the heavier elements fuse together. I haven't looked at the data to see if you'd actually get an interesting musical result, or if it would just pretty much be the same like continuous spectrum during the star's entire life. But I suspect you could do something pretty interesting with those data. That's a great question. Thank you.
Thank you.
Thank you for the great talk. It was really interesting, and I loved the energy behind it. So what I know of the visual domain for the human capability of discerning the resolution in the visual domain is quite narrower than the one that we could discernate in the sound domain. So the bandwidth in the sound domain and the ability of the human ear to distinguish different signals or data in the sound domain is much more precise than the visual one. And by sonifying the molecule, do you think that there is underlying data in the chemistry of these molecules that could be revealed or quote unquote show the hidden by generating sound from the molecules?
Yeah, that's a really excellent question, and it's definitely something that I've always been really interested in, but haven't really spent a lot of time researching that specific question. Again, because of my focus being more on creating musical representations of these of the original data I'm working with. I do think there's a lot of potential there, and even going back to the zinc versus iron and the other transition metal examples, that's perhaps not the best example, because you can also see that difference visually. It's very clear that zinc's spectrum is very bare compared to the other ones. But I think, I wouldn't be surprised if there are certain data sets that are much, and again, this is kind of what we've been finding in the in our preliminary work and the IRL doing molecular dynamics sonifications, especially when there's too much data to represent visually. I think adding that data to the sound domain can be a way to highlight some properties that might be hard to visualize. That's not exactly the answer to the question you asked. I also want to say that I do think that these spectra, these visual spectra, in my experience, actually listening to them, even the very complicated ones, although they're very subtle, it can actually sometimes be easier to like hear a difference than see a difference, because the visual display is also quite complex, and they're all just kind of these very complicated displays of colored lines. Of course, I have a very musical background and have sort of like trained my ear to hear these things. That's another factor, I think, is that if you're not really like trained as a musician or paying attention to differences of sound, you won't be as attuned to those. Just as if you're, if you don't have training, like if you're trained as an artist, you'll have a better ability to discern different colors and hues and things like that. But yeah, I'm still very interested in exploring that, and I don't think I have a great answer for you now for sort of chemical properties that I think the holy grail would be some sort of chemical property that like can only be really communicated through sound. That'd be awesome. So I'll let you know in a couple of years, hopefully. But yeah, thank you for the question. No more questions? Well,
Can you make
ah.
sound representation of complex molecules like proteins?
Sound. So there has been some work done on that, and yeah, so the approach I'm doing based on these this spectroscopy data can certainly be applied, because you can take a nuclear magnetic resonance spectrogram of a protein. It'll be very complicated, but you can get that data. I think that what might be more interesting for things like proteins are sonifying their interactions and their different geometries, and that's also something that we've started looking into in the Intangible Realities Laboratory. And David Glowacki actually has some papers from a few years ago of peptide chains being folded into different geometries and sonifications representing the energy of those. That's a different approach than what I'm taking, because it's not really using the spectroscopic data to make sound, but it's using this energy parameter and then translating that into audio somehow. But yeah, proteins and larger complex molecules is something that I would like to branch into eventually, but I feel like I've sort of started down this path of taking a very like first principles approach to the sounds of the molecular world. Like I'm really just working with atoms right now. So when people are like, what about molecules of the trillion atoms? I'm like, well, maybe I'll get to water first, and then I'll see what. Yeah, you might be interested in checking out that paper. Or there's also some work where people have created musical compositions based on like DNA codon sequences. Again, that's a bit more arbitrary musical mapping, but you can still generate different interesting musical patterns, and you can sort of hear, you can hear different genes or different patterns in DNA if the mapping is well done. Thank you. All right. If there's no more questions, then time for lunch. Thank you.